Getting into the topic, how do databases work? What is its internal workings and all? First of all, let's try to understand what is the actual assumption of people about a database. Right. Um, let's look into the illusion what people face that a database is a magical box that stores and retrieves data instantly. This is what usually people understand about database. But most of them don't even look into the internal workings, like what is happening or what is the core backbone of the database to be working efficiently and productively, right? So in order to understand that, we shall go ahead that we have recovery systems, concurrency control, memory structures, and disk files that are actually playing a key role for the smooth functioning of the database. And you might also understand what are the mandatory actions that has to be performed in a database. That is reads, writes, and also we require a lot of durability for the database to be functioning smoothly. Right. So the reality that has to be understood is that a heavily optimized coordination of algorithms, memory caches, and disk files designed to solve massive engineering constraints. So this is what the actual core reality what has to be understood about a database. Moving ahead, we will understand the physics of storage latency. Why do we prefer database? Why not something else? If I meant something else, then that includes a CPU cache, a RAM, SSD, HDD, and all. So let's try to understand what is the priority of which one. Right. So looking at a core axiom, the physical disk is painfully slow. Therefore, almost every database optimization exists to serve a single master goal, reducing random disk access. That is, suppose we have taken a code, SQL code like select star from storage, where type is equals to HDD and performance is equals to slow. That means here you can understand that usually the performance of HDD is very slow in order to either post or retrieve the data. So here you can try to understand what is the usual time consumed in order to post or retrieve the data or store the data indirectly. So you can try to understand the priority of the sources here. That is CPU cache comes in the first, and then RAM, and then SSD, and then HDD. So HDD is much more slower compared to RAM and all. Moving ahead, also we should try to understand the memory management and the buffer pool, right? What do you think when a query is written? Does it try to understand going through a single column or a single row or what? No, that is not the reality. Actually, the working is that it understood. I mean, it understands through pages. So you might wonder what are these pages here. Rows are stored and unordered in fixed size blocks called pages. That means pages are fixed size blocks of rows and columns, right? And in that way, memory is managed. The database caches frequently access pages here to serve future queries instantly, avoiding the slow disk. So the rule that has to be followed is that databases do not read or write individual rows. They move entire pages. That is, they get into the pages and try to understand what and where and how does it exist. And through that, any entire operation or any operation could be performed. Moving ahead, the retrieval bottleneck. What do you think? Suppose a book is required for some student and he gets into the library and try to understand if he goes to the library on his own and ask and looks for a book and it might consume a lot of time. But what if he goes to a or approaches a librarian and asks for a book? Then librarian, knowing uh, the entire setup of the library, he goes to the book directly and returns to you. Right. That is how the time consumption is also affected. It might be low or fast, but when you reach out to the librarian, then definitely a lot of time is saved. In that way, we shall be discussing how does a data being or something a data is being retrieved exactly, right? Now we should talk about complexities, that is time complexity. If we are going without an index, then the engine must perform a full table scan, pulling every single page from disk into memory to check for matches, which is terrible for millions of rows. But what if we are going through an index? That is an index scan. An index is a specialized, separate data structure built purely for fast lookup. It bypasses irrelevant pages, jumping straight to the target. That means we are directly reaching out to the target what we require rather than going into indirect routes, right? So we can compare the complexities, that is big O of n for the sequential scan and big O of log of n complexity for index scan. Moving ahead, so navigating the B-tree architecture. Now, why or how is this related to our database working, which has to be understood. So, why do we require the B-tree architecture? Why not a binary search tree? As you can see here, the entire flowchart, which is quite visible to you, BSTs are deep. Depth requires multiple hops, translating to multiple slow discretes. That means if we are choosing the binary search tree to be an architecture, then the reads are performed very slow. That means consuming a lot of time, and so it might bring some delay or latency. And that is the reason we choose B tree over binary search tree. Now, if you are choosing B tree, what is its advantage? It is highly disk optimized. Wide and shallow structure allows searching massive tables in just 3 to 4 discretes, through which we can definitely reduce the time. And clustered versus non-clustered. Clustered physically sorts the actual table. Non-clustered is a separate map pointing back to the unordered heap file. So this is why B tree is usually preferred upon binary search tree. Moving ahead, the query execution pipeline. Now imagine you're writing an SQL query and you're willing to understand how does it work or how is it understood, right? Here exactly you will understand the process that given any raw SQL query, that is SQL string, it usually is going through the parser. That is, each line or each word of the code is being understood first, and then it goes through the query optimizer. So here again, definitely we'll be focusing on cost-based optimization. That is how better or how it could be reached at low cost, right? So it evaluates statistics, cardinality, row distribution to dynamically choose the cheapest path. The hardest part of the database to build, that is query optimization, and then the execution plan exposes the optimizer's final decision, the critical diagnostic tool for performance tuning. So these are the main crucial methods through which SQL query undergoes and how the system understands. Moving ahead, connective tissue join internets. Now we have nested loop join, hash join, and merge join. But what has to be preferred and why it has to be preferred? We'll try to understand that much more deeply into this through this slide actually. So moving to the nested loop join, it is good for small tables. Having some small tables, then nested loop join could be preferred. And it would be terrible for large data sets and also resembling big O of n into m complexity. Every row in table A scans all of table B. Then why do we have to prefer hash join? Right. It is actually good to be used for large and unsorted sets. It builds an in-memory hash table of the smaller data set, then probes it for matches. Also, having merge join, you might try to understand why nested loop join nor hash join is preferred and why merge join has to be preferred. because bird join is usually preferred because it is extremely fast and highly efficient. Also, it is efficient where both data both data sets are actually pre-sorted. That means they are already sorted. So it requires both data sets to already be pre-sorted by an existing index before join. So the optimizer dynamically selects the mechanism based on table size, memory, and indexes among them. Moving ahead, concurrency and the asset guarantee. Now, you may have heard of asset, not the asset in the chemistry. Rather, you would also see the asset in the database management system. That is, A stands for atomicity, C stands for consistency, I stands for isolation, and D stands for durability. Now, what if you are actually deducting $100 from your account, right? And that is from going from your bank A, that is bank account A, and it definitely reaches out to the bank account B, whomever it might be. So imagine a system crash happens while you perform the payment, and you don't understand whether the $100 what has gone out of your bank account has reached the receiver or not. And that is where you will actually notice a system has crashed. Now, in order to solve these problems, the asset rules are actually followed. That is atomicity, all or nothing. Partial updates are rolled back using undo mechanisms. Either all are performed or nothing is performed. Consistency. Only valid state transitions are allowed. Rules are enforced. That means if you have just $100 in your account and if you have transferred to account from your account A, then it should not be showing that a negative balance is actually available in your account, right? A negative balance that states there is something but in a negative format, which is not at all existent in the real world. Coming to isolation, concurrent users cannot improperly interfere with each other's operations. That means, suppose a transaction is happening between account A and account B, and third account or a third user cannot interfere into this transaction. Committed durability, once committed, the data survives power failures. Right? Moving ahead, crash recovery via write ahead logging. Now suppose try to imagine or try to get into your childhood where you were attending the school classes and your attendance was actually captured. That is, the teacher, whoever is teaching you, would be definitely making a rough copy of the attendance first and then noting down into the register, right? In that way, it happens in the SQL also, that you will have to maintain a log file where each and every operation what you have written has to be noted there so as to implement it directly into the database. So getting into the topic into much more depth, right? We will understand it step by step. That is step one, sequential write, which is fast. The golden rule, before modifying the actual database pages on disk, the change must be written sequentially to the log file and then has to be gone to the data files on the physical disk. So try to understand there are again different types of logs, that is redo logs, undo logs, and also we have checkpoints. So trying to understand the redo logs, reapply committed operations missing from disk after a crash. And undo logs, rollback operations from transactions incomplete at the moment of failure. And coming to checkpoints, periodic flushing of dirty pages to disk to shorten recovery time. So this is how actually the accuracy of the data insertion or deletion has to be maintained or has to be understood while writing logs and writing logs before uh, really applying into the data files, right? Moving ahead, isolation levels and concurrency risk. So we shall understand that for the dirty reads, it is not actually visible when the read is uncommitted, And similarly, in the case of non-repeatable reads and phantom reads. And in the same way, you can try to understand the entire table, what it is actually conveying, right? So after understanding the table, you may get into the trade-off that concurrency inherently risks data anomalies. Locks solve this, but heavy locking destroys performance and causes deadlocks. Developers must trade strict safety for speed, right? Moving ahead, the modern standard, MVCC. Now, try to understand if there is a user A and he is trying to go through the data available or data that is visible to him, and there is some other user B who is actually manipulating the data, that is modifying the data. Now, should the manipulation be visible to the user A? It's definitely no, because in order to maintain the stability of the system, the reader can view the existing changes, and once the reader B actually makes the changes in the data, then that would be visible to the reader A. That means user A, right? And that is what actually conveyed here. Now, you can actually understand it through multi-version concurrent control. That is MVCC, as we told again. So instead of locking a row when read, PostgreSQL and MySQL maintain multiple historical versions of that row simultaneously. And the primary benefit that we achieve, readers do not block writers, and writers do not block readers. Unlocks massive scalability, and that lets mutual understanding between readers and writers. Moving ahead, distributed scale, replication, and sharding. Now, having lots of data in order to be retrieved or posted, there are two possible ways to be handling the data. Either it could be handled through multiple machines, or else it could be segregated different servers or different storage. Right? The replication is actually making duplicates. Copying copies the entire database across servers, solves read bottlenecks. And coming to sharding, splits the dataset into pieces required at massive scale when data exceeds a single machine's capacity. Right. Now, once again, try to understand that replication is making duplicates of the existing data. That is copying the data into multiple places or multiple stores. And sharding is what? Partitioning or segregating the data. Moving ahead, architecture by workload. Now, what does the workload mean? The workload in the sense how or what data is actually stored, right? OLTP, OLAP, and NoSQLs are actually different workloads. And OLTP, that is online transaction process, and OLAP, that is online analytic process, right? So let's get much deeper into this. Having OLTP, that is relational, that is row-wise, optimized for many small concurrent transactions, row-based storage. Examples, PostgreSQL, banking, and e-commerce. But coming to columnar storage, that is OLAP, optimized for massive aggregations, analytics, column-based storage. That is, in the real world, you make use of ClickHouse, Snowflake, reporting in order to store the data in different columns. Now coming to NoSQL, it is optimized for extreme speed, horizontal scaling, or flexible schemas. It might be either relational or columnar, and RAM-based or JSON. Now again, the real-time applications are Redis, MongoDB, high throughput feeds. Now, this has to be remembered that system design requires matching the engine's entire internal mechanics to the application's read or write behavior. There is no single perfect database. So the database are chosen based on the use or based on the purpose. Moving ahead, production execution and bottlenecks. That means let's try to understand what are the mistakes usually committed and how it has to be solved or resolved, right? Anti-patterns and bottlenecks. That is major mistakes that are usually committed. Select star. It pulls unnecessary columns, destroying memory caches, right? And missing indexes forces the engine into sequential full table scans. And now, in order to resolve these mistakes, we can cover the indexes and also pagination could be performed. That is, getting into covering indexes contains all requested columns by passing the table entirely. That is, without directly getting into the table entirely, we could also service the required ones. That is covering indexes. And pagination limits data retrieval bounds. Now, the other mistakes that are usually committed, M+1 query loops. Floods the network with thousands of microqueries and heavy log contention, transactions queuing between or behind a single exclusive log. Now, how this could be resolved? Explain pain plans. Always verify the optimizer's chosen path. And then also batch queries could be performed. That is, combine multiple inserts into single round trips. Now, the golden rule of optimization, what has to be strictly followed is that if the database is slow, it is almost always bound by physical disk input output operations or physical disk input output. So this has to be reminded as well, remembered in order to understand which database has to be used and how it has to be managed or handled to be efficient and productive. Moving ahead, the unified system model. So on a on an entire overview, we'll try to understand what exactly happens in the process. Given a query, the query has to be understood. That is through query optimization. Evaluates the cheapest execution plan. And then comes the B tree index instead of binary search tree, right? Finds the exact memory page in big O of login time and bypassing the slow disk. Now, the next one, MVCC engine, right? Creates a new row version safely so active readers are never blocked. And the last, that is writing the logs before performing it or implementing it directly. Write ahead log records the transaction sequentially for crash survival before updating the disk. So, understand in the big picture, modern databases are an orchestra of specialized mechanics. This invisible foundation safety runs banking systems, global cloud infrastructure, and the modern internet. So, you might try to understand databases are very much important in order to store the data. And having that, the importance has to be understood. Also, the importance of handling databases is also much more important.